Okay, so moving on from there, let's just talk about this again. So it's not moving on from there then. Um, so when we sample from our population, again, each sample is going to have its own mean. And the premise behind a lot of statistics is that those samples are going to vary in a normal distribution. So again, just a reminder, normal distribution is when you have this bell curve, and the farther away you get from the mean, the less likely you are to get that value. Well, the same thing applies with samples. So if you think about it, let's say our mean is again 20.13, whatever is being measured here, and we draw a sample from this population. Well, what do you think the most probable value of the sample is going to be? What is the most likely mean that we're going to get in our sample? It's going to be the most probable, not to say that it's highly probable, but the most probable is going to be the same as the population, right? So if we're drawing randomly from a sample with, or sorry, from a population with a mean of 20.13, then we're most likely have our sample have a mean of 20.13. And based on years of statisticians looking at this, that's generally what you find. There can be exceptions, but that's usually what you find. So if we draw from our population, and the population has a mean of 20.13, that's what we should get. That should be our most probable sample value. So that's what we have over here. This is the distribution of raw numbers, and this is the or scores in the population. This is the distribution of sample means on the right here. So again, the most probable thing that's going to happen is we're going to get a sample mean equal to the population mean. The second most, or other two, I guess, most likely sample means are going to be just a bit far away from, or not very far away rather, from that population mean. So chances are we're also going to get a lot of samples um, with scores just a little bit higher or a little bit lower than the actual population mean. So like 19, 23, kind of in that range there. Now, again, just like a normal distribution, the same logic applies to the extremes. So chances are if we get the chances of getting a sample mean that's quite far away from the actual population mean is much lower, at least much lower than getting something close to it. Okay. So in other words, in short, the sample means should result in about a normal distribution because they're drawn randomly from the population. And the more likely, it's more probable to get something closer to the actual population mean. And the further away you get from that population, the less likely it is. Let's look at one more example here. So this part on the left here is US male adult height in inches. I don't know how accurate it is, that doesn't really matter. This is a distribution of sample means, so the average in each sample we draw. Just like a normal distribution, the odds of getting something, so the actual average in the population is going to be 70 inches or 5'10", right? Well, it's pretty likely, again, because we're drawing from this sample, or from this population rather, to get our sample, that we're going to get something close to that, right? We're going to get 5'10" as the most common sample mean value, and then the further away we get from that, the less likely it is. So the odds of getting a sample mean of 6'5" is quite low because there aren't a lot of 6'5" people in the population we're drawing from, right? Okay. Well, the reason I'm spending so much time on this is that we use this or variations of this in our calculations. So we can this is obviously going to show up when we're running any kind of experiment or quasi-experiment, or even correlations, but I'm not sure if we'll talk about that. So we can actually get a sense of what's kind of the distribution that we'd expect. And that's going to have a lot to do with both standard error and our sample size, which we'll get to later. Okay. So one thing we can calculate is known as the standard error of the mean. And this is an estimate of the amount of variability in the sample means, or sampling error. So, okay, remember we talked about standard distribution, or standard error rather. Standard, did I say standard error? Sorry, I meant standard deviation. Standard deviation is kind of a measure of the difference between scores in either your population or your sample. So when we have height, one standard deviation is going to be, I think it's about 2.5 inches. So 2.5 inches, give or take. And that tells us how many of the values are going to fall in that range in our distribution. So let's say we have a standard deviation of about 2.5 inches. Well, that tells us that about 68% of the scores are going to fall either 2.5 inches above or 2.5 inches below that mean, right? 2 standard deviations is going to mean it's going to be about 5. This is not very exact, but about 5 away from that, 5 inches greater than or less than the mean, and so on and so forth. So that's to remember what we mean by standard deviation. What's kind of the typical amount that it's built off of how much the scores vary from each other, and that usually tells us if it's a normal distribution, if you remember that part, how much of the scores are going to fall within a certain range. Okay, so let's just again say my standard deviation for height was a whole foot. Well, then that would mean that 68% of the population is going to be between, say, 6'10" and 4'10". That's not the case, obviously, but just as an example, again, that's what standard deviation does. It tells us what is the range of scores, and we can use it to figure out where they're going to fall in what range. Well, you might see the connection that the same logic actually applies to sample means. Okay, so when we get the standard error of the mean, that's what we're doing basically. It's not just standard deviation, but it's standard deviation of the means of the samples. Okay. So for example, if I'm again looking at, so that I was kind of talking about individual scores there, but the same logic applies to sample means. So if my standard error of the mean is a certain value, I can use that to figure out what percentage of the sample means are going to fall within that range. Okay, so just like how I can look at a normal distribution of raw scores and say, well, okay, a standard deviation is like, we would say 2.5 inches, or is it 3 inches? This graph is kind of unclear. Let's say 3 inches. I know that a good chunk of the values are going to fall 3 inches above or 3 inches below the population mean. Well, the same logic applies to sample means. So when I get the standard error of the mean, it tells me what percentage of the values are going to fall within that range. So if I have a standard error of the mean of, say, 3 inches here, well, then I know that my sample means are all going to be, 68% of them rather, are going to be within plus or minus 1 of that standard deviation. Okay. We'll look at more examples of this. But again, standard error of the mean is how much variability is there going to be in your sample means. Okay. So again, if I draw 5 people, 10 people, or whatever number it is, we'll get to that too. The means of those samples, how much are they going to vary? Okay. So how do we get standard error of the mean? Well, we take the standard deviation and we divide it by the square root of sample size. Okay. So I have, let's say the standard deviation is 3 inches, and I divide it by the square root of my sample size. That will give me the standard error of the mean. And you could probably imagine how obviously standard deviation is going to affect this, and then also sample size is going to affect this. So let's say if we have a very big standard deviation, if we have a lot of variability within our individual scores, well, not surprisingly, that's going to result in bigger standard errors of the mean, right? So if you think about it, if there's really not a lot of, if the standard deviation is quite small in the raw scores of the population, so maybe one standard deviation is again like 3 inches. I guess that's relatively a small standard deviation. Well, then drawing people randomly from that population is going to give us less error in our sample means, right? In contrast, let's say we have a lot of standard deviation, or a big standard deviation score, and that's again the individual scores. Well, that's going to translate into a bigger standard deviation of the sample means, right? So if I have a lot of people, a lot of spread here, people are all across the board in terms of height, well, drawing randomly from that population is going to mean that the sample means are also going to vary quite a bit, right? Okay, but then so that's one big factor when it comes to how much your mean can vary. Your mean of your samples is the actual standard deviation of the scores themselves. But the other factor is going to be n, or also known as sample size. Actually, sample size also known as n. So the other premise is that the smaller your sample size, the greater likelihood that the sample mean will be different from the population mean. All right. Let's see. Let's look at an example of that. So let's say I draw only 2 people from this population here. What do you think the odds are of getting something far away from the true population mean of 70 inches or 5'10"? Well, it's going to be higher, right, than if I were to draw quite a few people. So if I draw only 2 people from this population, that's obviously a very small sample. I might get someone who's like 6'4", whatever 80 inches is, and I might get someone else who's like 75 inches, and then the sample mean would be pretty far away from the population mean, right? Whereas if I were to draw a lot more people, chances are it should be closer to the actual population mean. So if I draw 100 people from here, chances are I'm going to get a sample mean that's actually much closer to the population. To put it shortly, the bigger your sample size, the smaller your sampling error is going to be, and the smaller your standard error of the mean is going to be. Okay? With a big sample, you get smaller change in the sample means. Another way to think of this would be to say, if you were flipping a coin, let's say that you flipped it So in that situation, this is a bit different because it's not continuous variable. You either get heads or tails, but let's say the coin is fair. So you should get 50% heads, 50% tails, right? That's the population mean. As we know, hypothetically, if you were to flip it an infinite amount of times, it should be 50-50 exactly, if it's a fair coin. Now, let's say you were to flip it only 3 times. What are the odds of getting something that's far away from, that's not that 50-50 mark? Or 3 is a bad example. Let's say 4, because 3 is an odd number. Well, if you only flip it 4 times, you could get like 75% heads and only 25% tails. You could get 100% heads and only 0% tails. Because you're flipping it a very few amount of times, you might just be unlucky and get scores that are far away from the population mean, which is a 50-50 split. On the other hand, let's say you flip it 100 times or 1,000 times. Well, chances are there that you're going to get something pretty close to 50-50. It's not going to be, might not be perfect, but with a large number of people in your sample, or how many times you flip the coin, you're much more likely to be at least closer to that actual population mean of 50-50. So again, that's the premise behind, and that's why we divide by the square root of n, because we want to think about how our sample size is going to affect the standard error of the mean. Okay, so again, bigger sample size means less standard error of the mean. It means that our sample should be closer to the population. So again, you could just think of that as, let's say, I'm drawing from here, and these are my samples. Well, bigger samples is going to mean a tighter spread. So kind of a more narrow distribution here. If I have a smaller sample, it's going to get wider. Right? All right. Another thing we factor in is degrees of freedom. This is just n minus 1 or sample size minus 1. Don't really worry about this. It's not very important. It's just where in a sample, if you know with a known mean of this many points of data that are independent or free to vary from. So if you had 4 people go fishing, the mean of the first fish caught was 5, or mean number of fish caught was 5. Don't worry about this. It really doesn't matter that much. Basically, it's just affects the distribution, but you don't have to know the logic behind it really. Okay. Let's see. Okay. We'll take